So yeah, so we have, I'm nervous, oh Jesus Christ. So we have 0, we have hydrogen, we have, I'm not doing it in exact order, helium, we have lithium, we have carbon, nitrogen, oxygen, and it keeps on going. Calcium, phosphorus. They don't actually go out evenly, but what's interesting is there's actually no gaps in the periodic table. So that's pretty interesting. And what Mendeleev was able to do through his observations and distillation of the elements, he was able to actually predict elements that weren't discovered yet. And this is what most people talk about often, was that he understood how the characteristics and other features of, or characteristic properties of the elements, and he could predict ones that weren't discovered yet and were then, 100 years later. So that's an interesting thing in which by measuring and carefully measuring something, and there happens to be a gap, actually predicting what that gap would be filled with. And a lot of science actually does that. They do that with a question, what is this? Or they do it mathematically, they do it problem solving. Let me get this. Oh no, okay. All right, so how do we measure stuff? How do we measure the stuff of a leaf? So I don't remember what you said the tree was, but I did take a look at a leaf, the general leaf, and what I'd like to do is have the children collect 2 leaves from the tree, be nice to the tree, and take their leaf. I'm just cutting one out, and basically this is, I believe, the leaf shape, and measure the width of the leaf and the height of the leaf with one of the calipers. All right, just to go through the exercise of measuring something. And it would, I don't know, I mean, I'm just going to do something now in which I've sort of screwed up my order, I think, but anyway. But what I thought would do, what I forgot to mention is, with Mendeleev, one of the most important things he actually started to figure out was not only the weight of the elements, but in dealing with the properties, he was dealing with ratios. And ratio can be perhaps a complex topic for kids, but I think I can demonstrate it here on the clay tablet. So let's do some simple exploration here. And I don't know if I said this, but these instruments at one time were considered not drafting implements, but mathematical instruments. So what I'd like the student to do is actually to take the smallest divider, the Mendeleev water divider, and put one of the points into one of the corners and one of the points in the other corner. And then I'd like them to scribe an arc. Wait a second. Let me do that a little bit better. I've had a lot of coffee here. So it scribes very easily through the clay. I'm not really. And then in the opposing corner on the bottom, scribe another arc. Now with your divider, you'd like to measure measure this where the arcs intersect, and from there draw a line. And if you want, I think my thing shifted a little bit. I have to make these dividers a little bit more robust. And the other thing is there's a little piece of two pieces of rubber tire inner tube in the joint here, which creates some tension. But if they end up getting too loose, you turn it clockwise and it tightens it back up again, so it feels stiff. It could be a little bit too stiff, but it's really kind of nice. Feels right. So now that we've divided this, what's happened is we divided this into two equal halves. And having two halves, perfectly even halves, we have a ratio of 1 to 1. Now if we were to do this again, divide this in half, take your divider and put it in the base of this line and draw an arc, and then the opposite corner of the clay, draw another arc, measure this, and now we have divided this in half, which is then two halves. You can take the same measurement, bring it over here, and now we have 4 equal parts. So we have 4 equal sections, or 2 and 2, or 1 and 1. And all of those represent a ratio of 1 to 1. From here, you can determine a few other ratios, which is 1 to 1, 2, 3, 1 to 3. Now, what's interesting about ratios is most of the world of materials actually are ratios that are not 1 to 1. 1 to 1 is sort of a rarity. So most things, and one good example of a 1 to 1 ratio is pound cake. So 1 pound of flour to 1 pound of sugar. Another one, a rare 1-on-1 would be there's 2 days of the year, 2 days out of 365, in which daylight is the same length of time as night. So only twice a year does the 1 to 1 happen, where daylight is equal to night. So maybe you can think of a few 1 to 1 relationships But most things, like the material I was talking about, salt, is not one-to-one. Chlorine and sodium that make salt are not, it's not a one-to-one relationship. All right. So, I mean, I'm not going to do it right now because I think you guys are probably getting bored out of your minds, but I can stretch this into numeration, into architecture. So, you know, a clay tablet or a plaster slab was actually, you know, a drafting record in which actually things were designed and engineered on. Drafting was actually this kind of scribing, or mathematical scribing was actually part of engineering. So this could be a cathedral, an ark. You can take this clay slab and actually draw a floor plan. So I'm just making something up right now. So there's a doorway. The door opens out. So anyway, there's a ton of stuff. And obviously you can take materials, things that you find or collect, different things, width and height. So I could take the width. So I'll mark the width here. I can take the height. Let's say we'll start off this baseline. Then we can capture the width. I'm trying to do this fast, but in the height. Now we have the basically perimeter of a leaf inside here. And you can actually sit there and plot it and measure it out, or trace it. Or in this case, because it's clay, you can make an impression of the leaf right into the clay. So